Hi, my name's Ari, and today I'd like to share with you our work on the language of causation. The words we use matter. Each of these sentences conveys a different causal story about the relationship between Dr. Jones and the patient, and those stories have different moral and legal import for Dr. Jones. In the first, it sounds as if Dr. Jones ended the patient's life with malice, but the last suggests something less nefarious. Perhaps she supported the patient in voluntary euthanasia. In this project, we're interested in understanding how these subtle differences in language track meaningful differences in causal concepts. To try and get at this question, we designed a model that links people's causal language to their underlying causal concepts. Our model has three components: a causal inference component, a semantics component, and a pragmatics component. The causal inference component is based on the counterfactual simulation model, a quantitative account of causal reasoning. Say we wanted to judge causality in a case like this one, where A collides with B and B goes through the gate. The counterfactual simulation model assumes that we have a generative model for the domain of interest. And with that generative model, we can stage a counterfactual manipulation, and then run noisy simulations in the model to assess what would have happened in the counterfactual scenario. These counterfactual simulations allow us to assess A's causal role. Critically, different types of counterfactuals allow us to assess different aspects of causation. The counterfactual simulation model describes multiple different aspects of causation computed with different types of counterfactual contrasts. Here we utilize three: whether causation, which aligns with the traditional notion of counterfactual necessity; how causation, which tests a finer-grained notion of counterfactual dependence at the process level; and sufficient causation, which tests whether the candidate cause could have brought about the effect of its own doing. With this base causal knowledge, we're able to define a semantics. We define a semantics for four causal expressions: caused, enabled, affected, and made no difference. The expressions are defined as logical combinations of the aspect values. As we can see in this diagram, some of the expressions' meanings overlap in the space of causal concepts. This means the expressions are not mutually exclusive. Multiple verbs can be true of the same situation. This gives rise to an ambiguity, and in order to address that ambiguity, we augment our model with a pragmatic inference component. Our pragmatics model takes in the semantic representation of the scene and produces a judgment according to rational principles of communication. Specifically, our pragmatics model favors utterances that are both true and informative. So in a case like this one, where A knocks B through the gate, both caused and enabled are literally true. The semantics model sees them as equally good descriptions, but the pragmatics model favors the more informative caused. Once we have our model, we worked to test it empirically. We designed two tasks, a speaker task and a listener task. In the speaker task, we showed participants video clips like this one, and then asked participants to choose the causal description that they thought was best. In the listener task, we flipped the script. Participants were told that a describer had been viewing a scene and that they had selected one of the four given descriptions. The participant then had to rate which of two videos they thought the describer had been viewing on a slider. Our model does a good job explaining participant behavior in both these settings, capturing most of the variance in both paradigms. To get a better sense of what each component of the model contributed, we compared the full model against two lesioned alternatives: a no pragmatics alternative, where we remove the pragmatics module from the end of the pipeline, and a regression model that mapped directly from causal aspects to participant judgments. Both alternatives underperformed relative to the full model, suggesting that causal knowledge, semantics, and pragmatics are all an important part of the picture. Digging into these models a little bit more to get a better sense of why the full model performs better, we can look at individual cases. For example, in experiment 1, when participants saw this clip on the left where A knocks into B and B goes through the gate, they overwhelmingly said that A caused B to go through the gate was the best description. Our full model agrees. However, the semantics model, seeing that multiple descriptions are true, ends up rating them all differently, failing to capture participant behavior. On this case on the right, where A knocks into a box, knocking the box out of the way and allowing the B ball to go through the gate, participants overwhelmingly say that enabled is the best description. Again, our full model has the right idea, but here the regression gets things not quite right, underrating the extent to which participants favored the enabled expression. We see a similar story in experiment 2. In this trial, where we used the same clips as I was just discussing for the previous experiment and told participants that the describer had chosen the utterance enabled, the full model is able to make the correct judgment, where the no pragmatics model is again stuck between the two true clips, and the regression model doesn't quite capture how participants are thinking about how the verb is enabled. To sum up with some conclusions, in this work, we implemented a model aiming to link people's causal language to their causal concepts. We saw that our full model outperformed the Legioned alternatives in experimental tests, suggesting that each component tells us something important about the language of causation. And going forward, we'd like to continue to expand on this framework to account for more naturalistic descriptions. Thanks so much for your time.